orchestrated the construction of Advanced Virgo, and Advanced Virgo has been the antenna that joined Ligo in the first detections. Giovanni has been a pupil of Alberto Jazotto, who has been the father of Virgo, and another man of vision, speaking about Ray and Adalberto. And Giovanni is also a very competent person in almost all aspects of gravitational wave detectors, in particular of the interferometric type, and an extraordinary witness of the development of the field. So I am particularly pleased about his acceptance to give this lecture here, and I thank him in advance for all the things that he will teach us. Thank you, Giovanni. Go ahead.
So thank you, Innocenzo. Thank you, Salvatore. Thank you to all the organizers. The title I've been assigned is Virgo and the Contribution of Italian Physicists and Physics to Gravitational Wave Science. And I thought a lot about this title, and I would like to start with a disclaimer, which comes from this thinking. I will tell little in my seminar about contribution of single persons, and the reason is that the more I think to what has been my experience in the field, and the more I am convinced that, especially when you discuss experiments which are based on the developments of complex and new detectors, you easily understand that this is a collective enterprise. For sure, the contribution, the vision of brilliant person is there, and nobody can forgive it, but it's really something which can progress because there are groups, there are collaborations behind which in the end make it happen. Anyway, let's start. Between 2015 and 2017, in a couple of years.
Professor, sorry.
Yes.
Maybe you can share your screen.
Oh, sorry. Just a second. I thought I had already done it, but it seems it's not the case. So. Does it work?
Yes, thank you.
Oh, sorry again for the inconvenience. So, in just 2 years, we had 2 groundbreaking discoveries, which really started a new era in the observation of the universe. The first detection of gravitational waves, event called named GW 150914. And the first detection of a binary neutron star, followed by a multi-messenger observation of the event, GW 170817. These are the 2 events completely changed the scenarios for a research line, the experimental detection of observation of gravitational waves, which had been going on for decades as, let's say, an underdog in physics, which because basically was a research line which was considered by many people in the wide scientific community as desperate, as a research line with little chances of success. But after these 2 events, it became kind of mainstream in physics. In 2 years, some crucial results were achieved. The first detection of gravitational waves, the evidence that gravitational wave travels at the speed of light, new tests of Lorentz invariance, first test of gravitational wave polarization, test of general relativity in strong field regime, alternative measurement of the Hubble parameter, the first observations of binary black hole mergers, the evidence of a new population of black holes with higher masses, the first observation of a binary neutron-star merger, the first measurement of neutron-star tidal deformability, the link between gamma-ray bursts and neutron-star mergers, the evidence of kilonova being powered by binary neutron-star merger, the evidence of formation of AV elements after a binary neutron-star merger. So there is really a lot of physics, nuclear physics, astrophysics, cosmology descending by these two observations. Since then, a lot has happened. And this chart is just astonishing. I keep thinking it every time I looked at this chart. This represents the cumulative number of events observed by Ligo and Virgo. So it started with a few events in the first 2 runs, and then suddenly there was an abrupt change of slopes. And basically during the run, the observing run 03, which ended in March 2020, Ligo and Virgo were observing 1 event per week. So we have moved in a very short time from the era of discovery to the era of statistics and population studies, which can be as important as, if not more, than the first phase of these observations. And also this chart is quite impressive. Here, the blue circles represent the black holes discovered by Ligo and Virgo. As a function of their mass, which you read on the vertical axis, and you immediately see that if you compare it with the black holes discovered through electromagnetic observations, which are the purple dots, you are really observing a new population. Moreover, you start seeing also dots in that area between 2 and 5 solar masses, where in principle you should not be seeing too many objects, since it's a so-called first mass gap, where in principle you should not have neither neutron stars nor black holes. So it starts to be really, really interesting. Virgo, that you see in this photo, the European gravitational wave detectors, originally funded by France and Italy and realized in the countryside near Pisa, has been giving a crucial contribution to this learning that we are achieving. Let me just mention that today Virgo is run by the Virgo collaboration that is currently composed by about 700 members from 125 institutions of 15 countries. And 9 of these countries have a leading role in the Virgo steering committee. So beside the original France and Italy, we have the Netherlands, Poland, Hungary, Spain, Belgium, Germany, and Greece. So it's also the Virgo collaboration. It's become a large one. It was not like this when things started. So probably it's the right time to look back, try to understand the origin of this enterprise. And Italy has been playing a crucial role in the race towards gravitational wave detections. Already in the earlier times, when this race started with the resonant bar detectors, for which the first experimenters was Joe Weber, Italy had a crucial role in the development of cryogenic and ultracryogenic resonant detectors, and the initiator was Edoardo Amaldi, who is in this photo together with Guido Pizzella, who then they realized the Explorer detectors that later was run at CERN, and together with other pioneers in Italy, they gave a big contribution to the first ever gravitational wave network, which was named EGEC, and was composed by 5 resonant bars, cryogenic resonant bars around the world. Explorer, CERN, run by Guido Pizzella and the Roma group. Nautilus in Frascati, led by Eugenio Coccia. Auriga in Legnaro, led by Massimo Cerdonio, and then Niobe in Perth, led by David Blair, and Allegro in Louisiana, led by Warren Johnson. This was the first example of how detectors run by different collaborations can collaborate in order to draw the maximum scientific payoff out of the data. But in the early 60s, Pustovoit had proposed the idea of using interferometry to detect gravitational waves, and the concept there was to try to detect the effect of gravitational wave impinging on a ring of freely falling masses. Interferometry could, in fact, be the most sensitive way to detect such an effect. And the Einstein equation tells that if we replace some of these freely falling masses with mirrors and try to read their displacement using a laser, then the displacement of this mirror induced by gravitational wave is proportional to the amplitude of the wave, which is established by nature, times the arm length of the interferometer, which is established by men, and by their technological and funding capability. So this equation says that the longer is the interferometer, the most sensitive is the detector. But then you need to put some numbers to understand if you're really able to do it. And the numbers, typical numbers are the 2 neutron star coalescing at 10 megaparsec, which is approximately the distance of the Virgo cluster of galaxies, is 10 to the minus 21, so it's very small number. Feasible interferometer on Earth can be a few kilometers. You then are easily limited both by technology, but also by practical considerations, such as the difficulty to find a site with urbanization low enough, and you are limited by cost. So this means that the required sensitivity of your detector is delta L equal to 10 to the minus 18, 10 to the minus 19 meter, which is 1,000th of the diameter of an atomic nucleus. So you easily understand that you're trying to build a detector where you want to measure the displacement of a macroscopic object like a mirror by 10 to the minus 18 meter. And this immediately explains the challenge. This immediately explains why it took 100 years since the Einstein prediction to detect gravitational waves. Basically, the accuracy that you need is equivalent to measuring the distance to Proxima Centauri, which is 4.2 light years, with a precision of 10 microns. The first attempt to make a proposal for realizing a real experiment was put forward by Ray Weiss in 1972. You had the fortune to listen to him directly a couple of days ago. I would like to remark that this paper was never published. It remained an internal note of the MIT. And if you ask Ray why he never published this paper, which was basically the foundation of his future Nobel Prize, he tells you that at that time you used to publish the results of the experiments, not the plans for an experiment, which is interesting in a time in the time we are living in, where there is a race to publish, since academic careers are basically built on bibliometry. So it's an interesting and different point of view. A few years later, independently, these two men, Alberto Jazotto in Italy and Alain Breguier in France, were thinking of designing a detector for gravitational waves. And the two men luckily met once in Rome, and discussing together, walking around the Minerva fountain at the University La Sapienza, they came up with the idea of joining the forces and proposing an interferometric detector in Europe. That was a really lucky meeting because these two men had complementary competencies. Alain Breguier was an expert of laser. Adalberto was in fact a particle physics, but he was really fond of the idea of realizing, of finding the way to make an experiment which was sensitive enough in the low frequency region, and I will tell you why. But anyway, they put the forces together, and everything in Italy, this started in a small barrack, 4 meters by 3, in the NFN lab in San Piero a Grado, which was heated by an electric heater, as you see in this picture. And this was the early time when Adalberto Jazotto was trying to realize with a few collaborators a system, an active system to isolate mirrors from vibration. So this was how Virgo started in Italy. And if you think of what Virgo is today, is pretty impressive. Gives the idea that big dreams in science can really start in a small room, and then when you have the vision, when you have the competence, when you have the strength to pursue these dreams, they eventually can become real. In 1987, a few people, four groups in Italy and one group in France, made the first proposal to INFN only. And in fact, the proposal was written in Italian for an interferometric antenna for the research of gravitational waves. And I want to stress that in this proposal, so among the founder of Virgo, there was a group by the University of Napoli led by Leopoldo Milano, and there was Innocenzo Pinto from University di Salerno. So the University of Napoli and Salerno were among the founder of Virgo. And here you see Leopoldo Milano in this photo, who recently passed away together with Alberto Jazotto, and I'm really happy to remember these two men together. Then the Napoli group has covered, there has been a long story of contribution. Napoli group has covered many leading roles in Virgo, starting with Leopoldo, but that is a long history of contribution to Virgo. 2 years later, in 1989, together, two proposals were put forward to funding agencies: the Virgo project in Europe and the Ligo project in the US. And it's interesting to go back and read back these two proposals, because there was a long-term vision there. In the introduction of the Virgo proposal, Adalberto and Alain were writing that Virgo must be considered both as an experiment and as a step towards a future observatory. The long-term goal is being one component of the gravitational wave detectors network, which will involve other detectors in other countries and provide the data of astrophysical interest. And this will generate an international effort required by the birth of gravitational astronomy. So it was 1989, and these men had a vision strong and long enough to imagine that in the end there should have been a network, an international network of gravitational wave detectors. This is not obvious at all. This was not obvious at all, because basically there was a number of projects in competition that were being planned. And so having the idea that in the end you had to realize a network of collaborating detectors was not obvious at all. But Alain and Adalberto were writing that this was the way to get data of astrophysical interest. So if you think what happened in 2017, you see that there is some prophecy there. And I'm really impressed when I read it back. Adalberto Jazotto was the first, who is in the 80s already, was conceiving the idea of a detector with a low frequency threshold, so with a bandwidth larger towards the low frequency. He was at the time thinking about detecting continuous sources, and he thought he had the right idea to achieve the goal. Now we also know that low frequency are important not only for continuous sources, which in fact have not been detected yet, but they are important also to observe large mass black hole for a longer time. In any case, this idea of pursuing low frequency sensitivity has been very important for second generation detectors. So what was limiting that? This is limited by the fact that low frequency spectrum is dominated by seismic noise. Typically, seismic noise has a spectrum which roughly goes as alpha over f squared. At 10 Hertz, it has a typical amplitude of 10 to the minus 9 meter per root Hertz. You want to achieve a sensitivity of 10 to the minus 18 meter per root Hertz. So you need to suppress seismic noise by about 10 orders of magnitude, which is a lot. You have a simple way to do it, to just suspend the mirror as a pendulum. Then above the resonant frequency of the mirror of the pendulum, you will have a natural attenuation. If you build a multi-pendulum, you will get an attenuation which is steeper and steeper as a function of the number of pendulums that you use. And so what the Jazotto and the Pisa group were trying is to build a chain of pendulums capable of isolating vibration in 6 degrees of freedom. And the first technology that was attempted was the use, the real problem there is how you get the vertical isolation. Because the horizontal isolation is simply given by the pendulum equation, but then you need to also build a vertical oscillator which has a resonant frequency low enough. And so it must be able to sustain a big load, but at the same time being soft. And the first technology used was that of air springs. So basically, the pendulums were cylinders filled with gas and using bellows to provide using bellows to separate them from outside, provide a spring soft enough. And these in Pisa there were 2 super attenuators realized with this technology, with accelerometers and later interferometers reading the relative position in order to be able to measure the achieved attenuation. And the first measurement was, you see here, an historical photo of this super attenuator inside a green vacuum chamber. And the first result was that an isolation of 10 to the minus 9 was achieved at 10 Hertz, which was good, but still not enough. This system was too sensitive to temperature variations. So there was a technology change. It was the gas spring was replaced by so-called blade springs, so cantilever blades made in steel, coupled with magnetic anti-springs, which were able to reduce the vertical resonant frequency from 1.5 to about 0.3 Hertz. And this technology further improved in the next years was the one that is currently used in Virgo since the beginning, proved to be very, very effective. So in the end, the final super attenuator was realized, and it was capable of suppressing the vibration isolations of about 10 to the 15 at 10 Hertz. This was the key of the success of Virgo in the low frequency region. Then some history. As I said, the Virgo proposal was put forward in 1989. And at that time, the CNRS appointed a review committee chaired by Patrick Fleury, which was a well-known particle physics, and who provided a very positive report, which basically assessed the feasibility of the experiment, raising some doubt on the schedule. So he said many years will be needed to go from project to a real experiment. In 1982, Ligo was approved. In 1983, Virgo was approved by CNRS. Situation was a bit more complex in Italy, where INFN President Nicola Cabibbo was strongly supported, but there was some resistance in the organization. His mandate ended in 1983. Then Luciano Maiani was elected president, and also Luciano Maiani was very supported. And in next year, he was able to make Virgo approved by NFN. In 1985, there was another important step. A group from Rome, led by Fulvio Ricci, which was part of the Pizzella group in Explorer, joined Virgo. And this was important because basically there was the recognition that interferometry technology was most promising, so forces which were that far committed on resonant band detectors came to give a hand to make Virgo real. I want to quote here a sentence by Luciano Maiani, which is reported in a book recently published on the history of Virgo. He said, much of INFN took a dim view of Virgo because it didn't belong to the particle or nuclear physics fields, which have always been the organization's main area of interest. Seen in this light, it looked like a new competitor because it could have taken resources away from other experiments, and this created resistance. However, I was convinced that Virgo was a fundamental physics experiment that continued along the lines begun by Amaldi and that had a great tradition in Italy. For this reason, it had to be funded. Today, I know for certain that Virgo has given much to the INFN, also in terms of its reputation, because it has added an element of innovation that has benefited the organization. INFN studies fundamental physics, whatever the fields. So this is an important statement because we need to understand the background. Jazotto had gone in front of INFN proposing an experiment which didn't use accelerators, which didn't use drift chambers or vertex detectors. It used laser beam and photo detectors and mirrors. So it was really a cultural jump for INFN, although this was an experiment on gravity, and gravity is a fundamental force. So this is still about fundamental physics. So in the end, I think that INFN was able to make that jump and accept Virgo as one experiment to be funded. So the construction of Virgo could start only a few years later, because then there was the problem of getting the land for realizing the experiment. The site of Cascina had been already identified a few years before, but there was a lot of resistance by the landowner who were objecting to expropriation. And they also went to court There are funny stories about president of INFN being called in front of a tribunal because a lawyer had sued him, accusing him to cheat the Italian taxpayers, because clearly gravitational waves do not exist. It's known that they do not exist, so why taking money from taxpayer for realizing gravitational wave detectors? In the end, so Virgo has been realized in this area here, between the town of Cascina, close to Pisa and Livorno. It is interesting to compare the timeline of LIGO and Virgo, because LIGO was approved 2 years before, but in the end, taking into account the delays taken for acquiring the land, the construction of Virgo, the completion of Virgo was realized 4 years after LIGO. And so since then, there is a gap, and there has been a race in order to reduce this gap. At that time, the Virgo collaboration was finally composed by limited 11 groups, 5 in France and 6 in Italy, Firenze, Urbino, Frascati, Napoli, Perugia, Pisa, and Roma. So it was much smaller than it is today. There were about 80 physicists involved in Italy and France. Now, after the completion of the construction, when the interferometer starts operating, the sensitivity was much less than needed, and it took 6 years to move from the first interferometer lock, which happened in 2005, to the achievement of design sensitivity, which was eventually achieved in 2011. And this required gaining 7 orders of magnitude in sensitivity. And so, and the story for LIGO is very similar. The question is, why did it take so long? The first strawman answer is that, well, these machines were completely new. Nobody really knew how to make them work. But we can go a bit deeper, and we know that for these machines there was a theorist noise budget, and the theorist noise budget said, okay, look, this will be limited by seismic noise in a very low frequency range, by thermal noise in the intermediate range, and by the shot noise of the laser in the high frequency range. But then there is a real noise budget, which is, as usual, different from the theorist one, when you have a contribution of a huge number of noise sources to the final sensitivity. Most of them are called technical noises because well, you find electronic noise of several boards, you find magnetic noise, coupling with magnetic fields, eddy currents, and all this kind of issues that you have to tackle in order to make them not dominant and achieve a sensitivity which is eventually dominated by what you call fundamental noises. So it was, again, the first time that physicists had to cope with that, and it took the learning curve was rather slow. It was much faster when we realized the advanced detectors. Another crucial step in this story came in 2007 when Ligo and Virgo signed an MOU to share their data. This was really a major step towards gravitational wave astronomy, because until then, Ligo and Virgo had been operated as experimenting competition. But eventually, what had been prophesied by Jazotto and Brier in 1989 became reality. These detectors have an angular response which is close to being isotropic. They are not like telescope that can be pointed, so they have not localization capability by themselves. Having three detectors together allows you to point the source in the sky. And so this is really what you need in order to give triggers to the astronomers. But it is not only that, it's also there is also another significant aspect, that having more detectors improves the event significance and the time coverage, and so this is crucial to make real science out of gravitational waves. In the end, the first generation detectors reached their target sensitivity. You see here the sensitivities of the two Ligos in green and red, and sensitivity of Virgo. You see here that at high frequency, Ligo is more sensitive because it's longer. Low frequency, Virgo was more sensitive because it had super attenuators. But the message here is that this was a real breakthrough. Even if Ligo and Virgo did not measure gravitational wave in their first generation, achieving target sensitivity was a breakthrough because it really demonstrated the technologies. You had, I mean, you need to, again, think of the context. The context was a context of big skepticism that this machine could really, in the end, be able to become observatories. But in the end, these machines achieved the duty cycle, which was, in the case of Virgo, more than 80% of observing time, and the sensitivity, which was the one that had been foreseen at the time of the proposal. So this really gave the scientific community the impression that physicists were understanding the machine, were correctly predicting the noise, and could operate this machine for long times. So this also set the case for improving them. And there was a strong case for improving, because in these detectors, the number of events you detect is proportional to the sensitivities to the cube. So it's the cube of the distance at which you can detect an event times the observation time. So it's if you have the technology to improve your sensitivity, it's much more convenient to do it, since you gain much more, rather than stay at lower sensitivity for a long time. And this sets the case for realizing advanced detectors. Ligo and Virgo could search, for instance, for coalescing neutron stars as far as 50 million light years, which was not enough for gravitational wave detectors for detection, whereas they made plans for detectors which could look farther, 10 times more. So I would stop here, maybe open a first session of question and answer, then make 5-10 minutes break, and then go to the second part of my presentation. I leave you the floor.
Okay. So there are any questions or comments?
I have small question.
Yes, please.
Thank you for very interesting presentation. The question I want to ask you. I see that sensitivity of Virgo is larger, is better on low frequency than Ligo, and why these technologies was not transferred to Ligo, this super attenuator, or it was some untransferable Italian secrets?
No. Thank you for this question. I need to tell a story here. So, when LIGO started, at the time where both proposals were put forward, the dominating idea was that the first gravitational waves to be observed would come from supernovae. So in the kilohertz range. So LIGO was designed as a two-detector experiment in order to make coincidence and detect pulse signals in the kilohertz region from supernovae. And so there was no focus on the low frequency region. And so the first generation LIGO was born with the idea of...
Голова болит?
Say again?
Ну, слава Богу.
Oh, sorry.
Она хочет кушать, нет?
Нет, пока через 15 минут.
So the first generation LIGO was not focused on low frequency. Whereas, as I told, Alberto Jazotto had in mind the detection of pulsars, and so he invested a lot on R&D on the low frequency range. But then, once Virgo demonstrated low frequency, LIGO also pursued the idea of extending the bandwidth towards low frequency in the second generation detector. However, they had a group from Stanford led by Dan DeBra who was pursuing already a different technology based on active isolation. And the reason is that Dan DeBra was already had already a lot of expertise in that field, and he was proposing a different technology to LIGO. So LIGO has been pursuing a different technology, and now we have in advanced LIGO an active vibration isolation system, which is not as performant as the super attenuator, but had anyway the effect of pushing this seismic wall towards low frequency in LIGO also. That's the story.
Thank you very much.
You're welcome.
Hello. I do have
please.
a correlated question.
Please.
Okay. So first of all, thank you. A very interesting talk. So you said that instead of LIGO, Virgo had in mind as sources, possible sources, pulsars. But when you say this, you mean a pulsar coalescence events or a quadruple emission of a non-axisymmetric pulsar?
No, yes, I'm talking of the second source. So basically the idea is instead of pulsar, one should say rotating neutron stars as sources of gravitational waves. but at the time it was clear that the blind search of a rotating neutron star is too expensive, is computationally too expensive, because you need to subtract the Doppler effects. So the target, the real target at the time was the limited set of rotating neutron stars, which also are known for their electromagnetic, for their radio emission. And so,
so
the idea
targeted
was,
searches.
yeah, exactly.
Okay. Okay, thank you.
You're welcome.
Any other comments or questions?
Giovanni, I had a, oops.
Okay. I had one question.
Please.
Yeah, my name is Alberto Mukhopadhyay. I am speaking from India. So I just started working on gravitational wave astronomy this year under two physicists, one from IIT Gandhinagar and one from my own institute. Both of them have worked in gravitational wave astronomy. So my question is, there's a plan for building one detector in India also. So what will there be some technological transfer? Like I was listening to one lecture by Professor Kip Thorne, and he said that there would be a technological transfer of quantum non-location device that will reduce the noise. And my second question is, how would you remove the thermal noise? Have any progress been made to remove thermal noise?
Okay, so about the first question, I will answer it in the second part, since I will mention Ligo India as well. So be patient. We'll answer in the second part. About thermal noise, as I said, thermal noise was already a limiting source in the first generation experiment. So at that time, the effort done was mostly to do our best in the choice of the material of the mirrors and the coatings. But then the real advancement in that sense has been done with the advanced detector. So also on this, I will talk soon in the second part of my talk.
Thank you.
Innocenzo, you were asking something before?
Yes, I was curious about what is the data rate that the experiments are presently supplying. I mean, I think that there should be a few terabytes of data each day, especially, after 03, probably the data rate will be very sustained, and it will pose also a problem of what they call the big data, in the sense of storage, retrieval, handling, and fast algorithms for sieving the data.
Yeah, you're right. And we are not at the level of high energy physics in terms of storage and computing needs, but we are certainly intermediate experiment. And so in order to work, we need, computing is starting to be a big part of this experiment.
What they call the big data.
It will be more and more complex as the sensitivity increase, because, for instance, for the next run, we expect to have one event per day. And in fact, planning for new storage and CPU is one key aspect of the experiment so far. Indeed.
Thanks. Thank you.
So maybe we can, it's 1 p.m. Maybe we can break for, I don't know, I asked the organizer how long you want to break. It's 5 or 10 minutes and then reconvene and...
Giovanni, I mean, it's up to you, and I think that 10 minutes could be
10
a good
minutes,
choice.
okay. So we can win at 1 past 10? Sorry,
Yes.
10 past 1? Okay.
Yes,
Good.
fantastic. Thank
Talk to you soon. Bye-bye.
See you soon. Bye.
Hello, whenever you want. Question to the organizers. May I start again?
Of course.
Yes.
Okay, good. So, we stopped here. Virgo and Ligo reached the target sensitivity. They didn't detect gravitational waves. But meanwhile, there had been substantial progress on some technologies which promised the possibility to look 10 times further in the universe and this way have access to a number of potential sources which should have been 3 orders of magnitude bigger. And this is how the projects for upgrading LIGO and Virgo to second generation detectors were conceived. One important point to be mentioned is that the LIGO proposal of 1989 already contained the idea of an upgrade to a much sensitive detectors. This was very important. This again, there was a point of long-term vision, because once NSF approved LIGO, it was also in some way buying the idea of a further upgrade. And so this made possible to have a significant funding for research and development on second generation technologies. This was a very important point in the story. So I'm now talking of Advanced Virgo. Advanced LIGO was rather similar in terms of the technology used. So the main point is to move towards new mirrors which are heavier and use state-of-the-art polishing and coating. I will tell something more on this. Then second relevant point is to increase the power stored in the interferometer. Then, especially in the case of Virgo, which is it's an optical design more sensitive to optical aberration, there is the need of a system to thermally compensate for this optical aberration. The optical design is also changed by adding a so-called signal recycling mirrors. So there is a number of substantial improvements done in the two detectors. I would like to mention some of those. First of all, the mirror technology. This is an extreme technology. It's really state-of-the-art. Starting from the substrate material, which is fused silica with extremely pure fused silica, which has low mechanical losses, and this is a key to reducing thermal noise, low absorption, which is key because impurities absorb the laser power, and this leads to thermal deformation of the mirrors, and so degrading of the optical quality. And also low scattering, because scattering of photons, of unwanted photons, is one of the main sources of noise in the detector. The advanced Virgo mirrors are 35 centimeters in diameter, 20 centimeters thick, 42 kilograms. And the flatness that you can reach by polishing the surface is impressive. It's better than 0.5 nanometer RMS. You can achieve this by using a technology called ion beam milling. So basically you use a beam of ions to polish the surface. And these show an optical absorption less than 0.5 part per million, which is rather impressive. But then, basically, these are pieces of glass. In order to make them mirrors, you need to cover the surface with a coating, which gives the mirrors its optical properties. And coating is a very delicate matter because it's responsible for the largest part of thermal noise affecting the detector. Coating is made by alternating layers of high refraction index and low refraction index materials. And here I have to mention that Innocenzo Pinto, with his collaborators, has given a major contribution to understand how you can optimize the deposition of this material in order to preserve the optical features and at the same time reduce the thermal noise as much as possible. Anyway, a lot of research is on coatings. But with respect to the first generation, the coating thermal noise was improved, but it's still the dominating noise source in the mid-frequency range of the detectors. Then, still about thermal noise, there was a lot of research to reduce the suspension thermal noise. And so from first to second generation, the wires suspending the mirrors were, in the first generation we were using steel to replace the mirrors. In second generation, we are using fused silica fibers. And on this item, there was a long R&D being conducted in several places, for instance, Glasgow, MIT, and in Italy, Perugia, Firenze, Urbino were on the forefront of this research. Then the mirror has to be not only suspended but also controlled, and so sophisticated mechanics is needed to be able to couple this mirror to the vibration isolator and at the same time control it with a sufficiently low level of control noise. So there is an entire research line on the so-called payload for which the group of Rome, which is a group of Rome in Italy with contribution from Napoli, strongly committed. An important piece of technology is the vacuum, since LIGO and Virgo have the largest ultra high vacuum volumes in the world. And thanks to these technological breakthroughs, the two LIGO interferometers could make the first detection of gravitational waves that you heard about by Ray Weiss 2 days ago. One question here is why Virgo was not up at the time of the first detection, and this deals with the timelines. Basically, the story is that Advanced Virgo got funded 2 years after Advanced LIGO. And so, for instance, in spring 2013, while LIGO was already mounting the mirrors, suspending the mirrors, Virgo was still undergoing a Navy modification of its infrastructure to realize Advanced Virgo. On the other hand, if you compare the timelines of A LIGO and Advanced Virgo, the time to complete the project was basically the same. So the time between the moment in which the project was approved and the moment when it started taking data is the same in the case of the project. It's about 7.5 years. Another important information is about the funding. So Advanced LIGO was funded for more than $200 million plus a substantial in-kind contribution by Germany, UK, and Australia. Advanced Virgo was approved by about 22 million euros plus an in-kind contribution from the Netherlands. Clearly, there is a different counting methods here because the LIGO budget covers 2 interferometers and counts also the money for salaries of the people hired on the LIGO lab, which is not the case of Europe. But another striking point is the money for investment, for R&D investment, because over $60 million were invested in the US for R&D on second-generation technologies, which was really important for the development of the field. Anyway, on August 1st, 2017, Virgo joins LIGO in the observation run 02, and for the first time, we had 3 2G detectors acting as a single machine with, let me call it like this, pointing capability. Then at the time, we also had a multi-messenger network established. So before the observing run 03, LIGO and Virgo were sharing the information on the events with 93 astronomical groups managing over 200 instruments who had signed a memorandum of understanding with the LIGO-Virgo collaboration. Since 03, this became open. So the main data on events without details on the masses, but the main data on the localization and on the nature of the event were shared automatically with the wide community through circulars openly available. And 2 weeks after Virgo joined the run, there was the first 3 detector events detected both by the 2 LIGOs and Virgo. This was again binary black holes, And the interesting fact here is that if you consider the localization without Virgo, this is shown in this sky map. It's this big banana there. If you add Virgo, this shrinks a lot and becomes interesting for astronomical observation, because the field to be investigated is much smaller. 3 days later, there is an error here in the title. This is the GW 170817. 3 days later, advanced LIGO and Virgo detected a binary neutron star in spiral. This is a striking moment because these events last several tenths of seconds. And it is localized within 28 square degrees at 90% probability. And this small field of observation is vital for subsequent electromagnetic follow-up. The initial alert was given 27 minutes after detection. But what really was what was making this thrilling was that at the same time, the detection of a short gamma ray burst in an area of the sky compatible with the LIGO Virgo observation had been announced. In fact, it was announced first. This was immediately spreading excitement in the astronomical community, because it was thought since a long time that short gamma ray burst could have been associated to the coalescence of two neutron stars. And this is a comparison between the event detected by the gravitational waves detectors and the gamma ray burst detected by Fermi, the GBM experiment in Fermi and the integral. There is a discrepancy, a time gap of 1.7 seconds. So basically, the two events can be considered coincident. The story then is well known. There was the identification of the optical counterpart in a galaxy called anonymous galaxy called NGC 4993. Here you see the point which basically had lighten up. It was not present in the photos taken some days before, and the event was then observed in the optical, infrared, UV, X, and radio, and it was the basis for a number of physical observations. First of all, it was possible to estimate the Hubble parameter because binary neutron stars are so-called standard sirens. So from the waveform you can measure the luminosity distance of the event. Not only binary neutron stars, coalescing binaries are standard sirens. From the optical counterpart you can measure the redshift, and so you can easily estimate the Hubble parameter. I must mention that since the next speaker in this series will be Bernard Schutz, I must mention that the possibility of measuring the Hubble constant out of gravitational wave observation was first pointed by Bernard in a paper, Nature paper of, if I'm not wrong, 1986. So this became reality for the first time. The observation from this event is fall exactly in between the measurement done by Planck and shows, so does not solve the tension among these two measurements. And the error is still too large, but we are really looking forward to increase the statistics in such a way to shrink this error and be able in next year to tell something more about which possibly can help solving this tension. This was also the occasion to make an extraordinary fundamental physics measurement, because the fact that the gravitational wave and the gamma ray burst traveled for under 30 million years before being measured made possible to set constraints on the speed of gravitational waves. And we can now say that a speed of gravitational waves is equal to the speed of light with an error of 1 part on 10 to the 15, which is an amazing accuracy for an astrophysical measurement. Nuclear physics, the waveforms generated when two neutron stars coalesce keeps trace of the internal structure of a neutron star, because in the final phases of the coalescence, the star is tidally deformed, and this leaves a trace in the waveform. And this is dependent on the equation of state of nuclear matter in a neutron star. Now, there is a lot of theory there. We have plenty of models in the literature which predict either more compact or less compact stars. This event this event was enough to get rid of some of this model, but we still not accurate enough to measure the equation of star. You will need a much larger signal to noise ratio. But again, it's been the first time when through gravitational wave we could have access to nuclear physics, and this again opens a field of investigation which is very promising for the future, especially looking at the third generation detectors. Moreover, looking at the light curve from the optical source, we could observe that when the days passed, structure were appearing in the spectrum. And this, again, is a strong evidence for the kilonova model, and is an evidence for formation of AV elements. Now, we knew well that very light elements, hydrogen and helium, are a cosmological origin. We knew well that elements up to iron are synthesized in stars during their ordinary life and spread in the universe when a star explodes in a supernova. But we know little on nucleosynthesis of elements heavier than iron. Because their formation in stars does not explain the observed abundance. Now with this event, we have some evidence that this happens, formation of this element happens when two neutron stars coalesce. And in these events, very important elements such as iodine are formed, abundantly formed. And this, I mention iodine because it is an element crucial for life formation. So since then, as I told in the beginning, we have a large number of events being detected. We are starting to make population studies. And so it's time to look forward. Currently, Ligo and Virgo are acting as a network, and they are planning new runs together. And they are planning a progressive increase of sensitivity through another upgrade, which is implemented in two phases. In the case of Ligo, this is called A+. In the case of Virgo, this is called Advanced Virgo Plus. We are currently completed phase, the so-called phase 1. Kagra, the Japanese underground and cryogenic detector, has also joined the network. Cannot still provide a sensitivity interesting enough for making science, but we hope it can soon happen. And in the mid of this decade, we should also have a fifth detector in India called the Ligo India, which basically will make use of the technologies developed at Ligo and infrastructure provided by the Indian government. So we will hopefully have, at the end of this decade, a 5-detector network, which promise to increase more and more the angular accuracy at which we will be able to localize events. A few more words on Advanced Virgo. This is based again on as it happened for Advanced Virgo, on the improvement of technology. Again, we are going to change the mirrors and have improved coatings. But at the same time, we will have larger masses. We will now use mirrors of 100 kilograms with a larger diameter, which will allow to increase the beam spot of the mirror and thus naturally reduce thermal noise. But we look forward. We look forward to third generation, where two large projects are being designed. Einstein Telescope in Europe, that in the current configuration is a triangular infrastructure underground, 10 kilometers length, hosting 6 different interferometers. And Cosmic Explorers in the US, which is an above-ground detectors. In the current proposal, it is made of 2 L-shaped detectors, one of 40 kilometers, a second of 20 kilometers. So this is opening the way to a substantial improvement of sensitivity. Let me say, up to now, the furthest event detected by Virgo and Ligo as a redshift of 0.8. With the A+ Advanced Virgo Plus project, we can go as far as redshift 2. With the third generation, we can go as far as redshift 10 or 10-ish, and this makes a substantial difference, because this instrument will really be able to make cosmology, and it will be a substantial change from second to third generation. An historical note: when Galileo first pointed his cannocchiale to Saturnus, he was reporting his observation in form of a drawing, and this is what he saw. He was talking of Saturnus Triformis. 6 years later, working on improving his telescope, he came closer to identifying the rings. He didn't walk the final step. This was made by Huygens years later. But basically, this is with the current gravitational wave detectors, we are in this situation. We ran them from a first generation. We then had the second generation, and we improved a lot our sensitivity. But then now what we can see using the Hubble telescope is this image of Saturnus with, we can even observe polar aurora, so interaction of cosmic rays with Saturnus' atmosphere. And we want to get from here to here, and third generation detectors are first steps toward this. The aspect which I find most striking of the recent observations is that we have really opened something new, and we have really opened a research field which is moving its first steps. It's different from high energy physics, because high energy physics has been making discoveries in the last many decades, and now it's getting more and more difficult, because you need larger and larger investments in order to make a step forward. Whereas in gravitational waves, this is really starting now. So it's very exciting in this sense. And I want to conclude with a sentence by Alberto Jazotto, who used to say, "Detecting gravitational waves, no idea could be crazier. But in the end, we have done it." Thank you for your attention.
Thank you so much, Giovanni. It was really a wonderful presentation. And thank you also for referring to our work in Naples and to mine in particular. I would like to ask the people to make all kinds of questions that they may have in mind, always, because there are no naive questions at all. All questions are interesting, and every question can shed further lights on many aspects. So I encourage everybody to make questions.
Hello, I do have a very short, more of a question. It's like, I'm curious about something. And the thing is that in all the detectors that you spoke about, there was never a mention of Geo 600. So what is? Because then I know that now it plays a different role than actually a detector that has to see this kind of events. But what was originally the idea behind the project of Geo 600, if you want to say something about it?
Yes, I really thank you for this question, because you're right, it was not mentioned because I was focusing on the scientific results, but Geo 600 played a crucial role in the development of the field. Not only, Geo 600 had behind a fantastic team of scientists in Germany and in UK, and they gave. Originally, they were planning to make 3 kilometers detectors, which eventually was not funded. So they made Geo 600. It was too short to give a real contribution in terms of sensitivity, but it was the place where crucial technologies were developed for the first time. So I was mentioning, for instance, the technology of fused silica suspension for the mirror. This technology was tested for the first time in Geo 600. Then they for the first time developed some noise hunting techniques that they shared with the rest of the community, so that we have been using in Virgo and Ligo. They also developed for the first time a squeezer, and in Virgo today we are using the squeezer developed by the Hanover group. First time for Geo, and they are collaborating with us, and this squeezer is regularly running on Virgo, improving our high frequency noise. So we are really, the entire gravitational wave community, the entire scientific community must be grateful to what Geo 600 has realized. And I also want to stress that together with them, we are working to realize and have approved the Einstein Telescope project.
Okay, thank you.
Any more questions?
I have a small question. It's this question is not correct, maybe, but what do you think about this proposals of Einstein Telescope and Cosmic Explorer? Which proposal is more perspective from your point of view?
Well, it's a very, very interesting question, and discussion is open. I think there are pros and cons with both proposals. Having worked at Virgo, having worked with the interferometer noise, I think that going underground, realizing a detector underground could be a very strong asset, because it really helps reducing environmental noises in general, which can really spoil the sensitivity. And since the ambition of the sensitivity is to improve it further and further, it could be really important to get rid of the largest environmental noises going underground. On the other hand, I think that Cosmic Explorer has the advantage of bigger simplicity, at least in the original configuration, since It starts with using known technologies. It starts without cryogenic, for instance, and so it might be simpler to implement in the earlier phase. And it points, it focuses on increasing a lot the detector lengths in order to increase the sensitivity. So both approaches are interesting and they have pros and cons. But I also believe that both projects now that have been proposed, there will still be many years before they are realized. So I'm strongly convinced that both of them will evolve, and they will influence each other. And I think that in 2-3 years from now, we will have improved proposals on both sides.
Thank you.
More questions?
There was a raised hand in the audience.
Yes.
And we also have a question from YouTube. But please, go on.
No. Go ahead, please.
Yes, it was me. Can you hear me?
Yes, sir.
Yes. So, well, first of all, thank you very much for the very interesting talk. It was really nice to see like a bit of history of how Virgo started. I have a very short question. Is about. So you say that the original idea was for when the Virgo project started was to detect a continuous wave of rapidly rotating neutron stars, but so far I think we didn't detect them. Do you have any idea if in the next observing runs we will have enough sensitivity to detect something, or if we have to wait for the new generation telescopes?
Well, this is hard to say because basically what we don't know in the end is what is the ellipticity of these objects. So we keep analyzing data, and I think it's possible that in the next run we detect something, and it's the same way possible that we don't detect something. This is really something we have to learn from nature. What we can do is do our best to improve the sensitivity in the low frequency region and observe for a longer time. And in the end, we will find something.
Thank you.
Any other question?
There was one question from YouTube. I'm going to read it now. Okay, it goes, is it possible to suppress the noise at high frequencies, kilohertz? The person is saying, even further, this could be important to detect post-merger frequencies of BNS merger remnants. Are there plans towards this for Virgo? This is by Silinde.
Okay, for these detectors, we are trying to act in the direction. What we are doing is to increase further the laser power and improve the so-called squeezing. Squeezing is a quantum technique, a quantum effect that we produce, which basically reduces the shot noise without increasing the laser power. But we do both. And so in the next run, we expect a significant further reduction of high frequency sensitivity, which goes in the direction you mentioned.
Thank you.
Any other question? Well, I had a couple. Oh, I think that I see a raised hand by.
Yeah.
Yeah, please go ahead.
Yes. Speaking of quantum noise, does Virgo uses quantum non-demolition technology to reduce the quantum fluctuation in the mirror?
Yes, Virgo uses squeezed light through a squeezer, which, as I said, was developed in Hanover. But in Advanced Virgo Plus, we will improve this further because we will be using the so-called frequency-dependent squeezing. I try to explain what I mean. So, in ordinary squeezing, what you do is you improve your phase noise by worsening the amplitude noise on the light. And you do this because this allows you to reduce the shot noise at high frequency at the expenses of worsening the radiation pressure fluctuations at lower frequency. But this radiation pressure noise is still dominated by other noise sources, so you don't care. However, in the next version of the detector, this radiation pressure noise can become important as well. So what we try to do is to use a kind of squeezing which is dependent on frequency. So at high frequency, you compress the phase noise. But as you move to lower frequency, you compress the amplitude noise. And so this gives you the possibility to use quantum effects to improve your sensitivity in the whole frequency range.
I just wanted to make a short comment. In the age of resonant experiments, there was an interesting proposal made by Professor Hirakawa from Tokyo, that of constructing an adjustable frequency resonant detectors.
Sorry, Innocenzo, the connection had gone, so I lost the first part of your question.
Yeah, it was rather a comment. Well, let me put it in a rather different way. Speaking about the contributions of the GEO group, they also suggested the possibility of operating an interferometer in a narrow band mode of operation. In principle, this might be interesting, especially for rotating neutron stars. And I was remembering that in the age
I've lost Innocenzo.
Yes, I think it's on his side.
Okay, it's not me.
Yeah. So since it's taken a while, if in the meantime we have other questions or comments, maybe we can take those in the meantime.
Yeah.
If there are.
Maybe is lost forever.
No, I just rejoined.
Okay, ciao Innocenzo.
I'm sorry, but no, I will try to make it shorter. When you spoke about the contribution of the Geo group, one thing that remarkable that I suggested was also the possibility of operating an interferometer in a narrowband mode. Maybe that would be especially appropriate for a rotating neutron star source. And in this connection, it came to my mind an early attempt made by the Japanese group led by Professor Hirakawa many decades ago to construct a resonant detector that was actively tuned on the fiducial frequency of the Krebs pulsar. And the underlying idea was to observe a pulsar in the electromagnetic spectrum and use the electromagnetic frequency to detect, to tune actively the gravitational detector in a narrowband mode. So this was my comment, my piece of memory. And my question was, do you think it might be possible to operate the big interferometers in narrowband mode as well?
Well, we have this possibility since we have a signal recycling mirror. This has never been done so far. First of all, because in the end, we are collecting most of the results from coalescing binary, and so nobody will choose at this stage to sacrifice that for a single source. On the other hand, probably in the future, if you know for sure there is a source, you can choose to optimize one detector and that frequency in order to study it better. That can be a choice to be done. Once you have a network with 5 detectors, there is a lot you can imagine, because you can also specialize some detectors to do some different things,
Yeah.
The other point was that, it's not straightforward from the commissioning point of view to tune a detector on a single frequency. So that requires some commissioning work, which takes time. But we'll see in the future. I don't think this is excluded.
Thank you. Any more questions? Marco, do you see any question on the YouTube channel?
No, not for now.
Okay. So maybe, is there anyone else who wants to ask a question? I don't see any other raised hand, so probably there are no questions left. And if this is the case, I would like to thank again Professor Losurdo for this really beautiful presentation. I think this is one of the best presentations that I listened to ever. So thank you very much, Giovanni, for your presentation and for accepting our invitation.
Let's hope that soon it will be possible to make something similar in presence.
Yes. I will get my second vaccine in 3 days from now, and hopefully I will end my jail soon. Okay.
Okay.
Bye-bye. Thank you so much, Professor.
Bye-bye. Thank you also to all.
Bye-bye.
Our thanks also to all the students. The next lecture will be on 2 p.m. the day after tomorrow. Generally speaking, all lessons will be each another day, and they will be alternating between 12 and 2 p.m. But please check on the web page of the school, because there have been some changes in the timetable, and so please check every day.
Bye-bye.
Yes,
Thank
just
you very much.
to touch on this, Friday should be at 4 p.m. Just
Okay.
to let the students know. All right.
Okay. Thanks a lot.
Thank you. Bye.
Goodbye, everybody.
Bye-bye.
Bye.